Okay, so I'd like to go through some of the theory behind this week's practical. And I'll go through three systems, actually, all of which are oscillating systems. And I'm just going to give you the really basic theory. If you want, of course, know more, you should read chapter 15 on oscillations from your textbook. But let me just give you the real basics that you're going to need for today's practical. Okay, so the first system is the horizontal mass on a spring. So we can draw a wall. Here is a spring. Here is the mass, and here's it's on a frictionless horizontal surface. The spring is spring constant K. The mass has a mass M. And what we do is we define the x equals 0 when the spring is in equilibrium. And then, so if you now move the mass to the right, some distance x, there's going to be a force of the spring on the mass, which is negative. So we'll say towards left, negative kx. And remember, F equals ma, Newton's law. If that's the only force, since it's frictionless surface on the mass, then that's equal to the force on the spring. Remember that acceleration is d squared x by dt squared equals negative kx. And now I'm going to use the notation of d by dt as just a little dot on top of the variable. So we can write x double dot equals negative kx. And then we can divide both sides by m. You get that x double dot equals negative k over m, which is constant, times x. That's a second order differential equation. The trial solution is x equals a times cosine of omega t plus phi naught, where a, omega, and phi naught are some constants. And we can just try that solution. So let's write down the various derivatives. So there's x. The time derivative of cosine is negative, derivative of cosine is negative sine. And you've got an omega in there on the t, so that comes out. So you get negative a omega times sine of that same argument. Now to another time derivative, the derivative of sine is positive cos, and so the negative sign remains, and you get another omega, so you get negative a omega squared times cosine. And so if you plug x into that this differential equation, you plug x dot in, then the whole thing works beautifully. So it is true if omega squared is the same as k over m. So this is a solution. A and phi naught are arbitrary constants, and these are related to the initial conditions of the motion. But omega is not arbitrary. Omega must be the square root of k over m. We call it omega the angular frequency of the motion, since it is the frequency of oscillations, but it's measured in radians per second. And omega is related to the period t by omega equals 2 pi over t. Okay, so that's the first system. Oscillating system. Next oscillating system. We're going to do vertical mass on a spring. So instead of a wall, we've got a ceiling. And let's just look at the spring alone. So if we hang a spring from a ceiling, sort of a massless ideal spring, then the spring will have a length. So right at the end of the spring, there's a spring-only equilibrium. So keep that in mind. Then, now we want to hang a mass off of it. And so this is a hanging mass, but we're going to leave it very gently in its equilibrium position. So it's going to stretch the spring by some extra amount, delta y. And in equilibrium, the spring force, the upward spring force, is going to be equal to the downward force of gravity mg on that mass. That's an absolute value there in this in the spring force. So k times delta y is equal to mg. You can solve out for what delta y is, mg over k. But what we're going to do, the trick here, is to define y equals 0 at this new equilibrium. Well, I'm not going to go through the math, but in this case it turns out that y does equal a times cosine omega t plus phi naught. It's simple harmonic motion all over again. And actually omega here must equal the square root of k over m. it's the exact same solution as the horizontal spring, but just you have to keep track of this new equilibrium position. Oscillates around the new equilibrium. Okay, third system is the pendulum. So here you got a mass. It's on a string or a massless rod or something. There is a ceiling here with a frictionless pivot. There's that mass at the end. You've got the length of from the frictionless pivot to the mass is L, and then you got it can move in a circular path, right? So we can define from the vertically down position an angle theta. So the position of the pendulum is actually an angle here. Once again, it turns out, I'm not going to go through the math, but if theta is small, so if theta max is less than around 10 degrees, then the motion is approximately, again, simple harmonic motion. Theta equals this amplitude, theta max, times cosine omega t plus phi naught, where phi naught is an arbitrary constant. So phi naught and theta max are determined by the initial conditions, and it turns out in this case that omega equals the square root of g over L, where g is the acceleration due to gravity and L is the length of the pendulum, and it turns out the mass doesn't matter in this case. So that's the basic theory behind this week's practical.